Welcome. In this lesson, we are going to introduce systems of differential equations. Previously, we've studied individual differential equations that have modeled one dependent variable at a time, but it's often the case that we have, for example, competing species, a predator-prey situation where we want to model the evolution of both populations and they perhaps affect each other. The prey affects the predator by providing a food source, but the predator consumes the prey, so they affect one another's rates of change. Also, if we have multiple lakes running into each other and we want to model a contaminant flowing through those lakes, then it would make sense for us to have the ability to model the amount in each of those individual lakes. So we're going to focus on studying two differential equations at a time, especially at the beginning of our analysis, and we're going to assume that these variables, that x can depend, or dx dt is a function of potentially t, x, and y. Before, without having two differential equations, we would have said that dx dt is a function of t and x, or the dy dt is a function of t and y, but we've never had the situation where we have more than one input variable. And that shouldn't pose much of a problem for us because we are interested in how these two things interact. So if I were to draw my two dependent variables, I have two dependent variables, x and y. This could represent the number of prey, the number of predators, and both of their rates are determined by time, but they also may be related to one another. And that's what we're allowing for the possibility of. So we have a number of different types of systems of differential equations. One is called a completely decoupled system. So suppose Ann and Bill both open bank accounts. Ann's pays 4% interest each year with an initial deposit of $250, and Bill's pays 3% interest per year with an initial deposit of $300. Then, if A represents Ann's balance and B represents Bill's balance, both as a function of t in years, then it follows that the change in Ann's balance in dollars per year is going to increase by 4% of whatever her current balance is. For Bill, that's going to be 3% of his current balance, A of 0, that is, Ann's initial balance is $250 and Bill's is $300. So the reason we call this system completely decoupled is because the rates of change do not depend on the other variable. For example, we see that A, its rate of change, is only dependent upon the value of A. The rate of change of B is only dependent on the value of B. And these are decoupled in the sense that they're not paired. When we think about a couple, we think about them as being together or related. But these are unrelated. It just so happens that they both model balances, and so it makes sense for us to analyze them collectively, especially if we want to compare their balances over time. We see that Ann's money is growing faster, but she has less to start. Bill's balance is growing slower, but he has more to start. So we want to maybe analyze what's going to happen to their balances in the long run. So this is a completely decoupled system since neither rate depends on the value of the other dependent variable. This type of system can be solved by solving each ODE independently. In fact, there isn't much to do here because if we could solve this by itself with separation of variables, then we would end up with A of t equals k e to the 0.04t. And that's, again, A equaling that means that the only function whose derivative equals 0.04 of its original function is going to be of exponential form. And then given that A of 0 equals 250, we make those substitutions in there, solve for k, and we get A of t equals 250 e to the 0.04t. For B of t, similar process. For B of t, it's going to be k e to the 0.03t. And we probably should distinguish between these k's. Not that we're going to end up using them collectively, but we probably should call this k sub A, and maybe we should call this k sub B, just to emphasize that they're not the same initial values. And you'll see later on that the k's actually do end up mixing into one another for non-partially decoupled systems. So B of 0 is 300, and making those substitutions, 300 for B, 0 for t, we get k of 300, and so B of t is equal to 300 e to the 0.03t. So if we take a look at a graph of these functions now, So here we have, in red, we have Anne's balance. And here we have Bill's function. And the reason we know that from this is because Bill's balance starts off higher. But you can see it grows at a slower rate, and the difference between their two functions gets smaller and smaller and smaller. And then eventually, at some point here, Anne's balance exceeds Bill's balance. And so it's of interest to us to be able to conduct this analysis so that we can see over time what's going to happen, especially if we're interested in these specific two people. So that's a completely decoupled system. We also have partially decoupled systems, and those are where one of the differential equations depends on the dependent variable of the other, but not vice versa. So let's take a look at a modeling problem, and we'll build a model and we'll see why this becomes partially decoupled. But I'll give you a quick example here before we get into this of what a decoupled equation would look like. This system right here would be considered partially decoupled because, as we can see here, the value of the rate of change of x, it only depends upon itself. And so it is decoupled from y. It does not have any, there's no y value affecting the rate of change of x. But if we look at the y, or dy dt, then we need information about x and we need information by y. So in a way they are kind of coupled, but they're only partially coupled because only y, the rate of change of y depends on x, but the rate of change of x only depends upon x. So let's suppose that we have two buckets, and I'm just going to kind of draw these two buckets. So here's a bucket, and then maybe here's another bucket. And what we have going on is we have the first bucket receives water at a rate of 3 gallons per minute with a concentration of salt of 1/4 pounds per gallon. So what we have coming into this bucket, and it doesn't really matter where we draw this arrow, but we have 3 gallons per minute concentrated with 1/4 or 0.25 pounds for every 1 gallon. So if you think about this, if 3 gallons come in every minute and you get 1/4 of a pound of salt for every gallon, so in 1 minute you're going to get 3/4 pounds, and that comes out to 0.75, which is the same thing as multiplying these together. What we have going out of this bucket is water flows out of the bottom of the bucket at the same rate into the second bucket. And I suppose to make this drawing a little bit more conducive to reality is let's bump this down a little bit so it looks like we're using the effects of gravity. And so what we're going to have this outflow coming into this second bucket, and it flows out of the bottom of the bucket at the same rate into a second bucket. So the water is going to still come out at 3 gallons per 1 minute, and that should tell us already that the water level is going to stay the same. The water level is neither going to rise nor fall. From the second bucket, the mixture flows out to another source at the same rate. Salt water comes in. Both buckets initially contain 5 gallons. So let's refer to some, and then so out of here we're going to have 3 gallons per 1 minute as well. So this is hopefully looking familiar as a modeling problem, at least with the initial bucket. And then for the second bucket, we'll kind of have to do the same thing. So we're going to define our variables here. Let's go ahead and call x. Let that be the amount of salt in bucket 1. That's going to be measured in pounds. And we'll say y represents the amount of salt in bucket 2, again measured in pounds. And t is going to be time in minutes, since we started pouring the salt solution in. So when we're going to try to model two rate equations. One's going to be dx dt, and the other is going to be dy dt. So dx dt, based on my definitions for x and t, it has to be in pounds per minute. Okay, so this is going to be a similar modeling problem. Here we if we multiply gallons per minute times pounds per gallon, we're going to end up with pounds per minute. And so this equals, let me go do this in a different color, this equals 0.75 pounds per 1 minute. And so that's what I have actually coming in, which is 0.75 pounds per minute. And then what I have coming out, well, I have 3 gallons per 1 minute. As we've already mentioned, this is X, the amount of salt that's in the bucket. That's already in pounds. And then we should also point out that these buckets are always fixed at 5 gallons. So X is, in terms of the flow rate, I have 3 gallons per 1 minute, but I can't just put 3 here because that measures gallons per minute, not pounds per minute. So I need to multiply this by some number of pounds per some number of gallons. Well, that's just my concentration of what's inside the bucket. What's coming out is a function of what's inside. What's inside of here? Well, at any moment, there are X pounds. And we can't say it's a quarter because, remember, there's stuff coming in and stuff coming out. So this is constantly mixing, and at any given moment, it's impossible to say exactly how many pounds there are in there without doing some calculus analysis. And so there are X pounds dissolved in 5 gallons. And you can see here we get pounds per minute again. So we have 3x over 5, or 3/5 x, which is 0.6x, and this will be in pounds per minute. So this will be my 0.6x. For dy dt, we're going to do a similar analysis. But for dy dt, what's coming in to the second bucket is actually exactly what is coming out of the first bucket. So this arrow here comes out of bucket 1 and enters bucket 2. So the inflow is the outflow of bucket 1, and that's going to be a positive 0.6x because 0.6x is coming in to the second bucket. And here I have to do the same analysis I did up here. That should be pretty straightforward for us to write. That's going to be y pounds. So what's coming out of bucket 2 is there are y pounds mixed evenly throughout 5 gallons, which will, again, in this case, will give us 0.6y. So this equals 0.6y pounds per minute. And then lastly, I will just subtract away that 0.6y here. And you can see now that we have a decoupled system. A partially decoupled system. That is, we notice that the rate of change of x, dx dt only depends on x, but dy dt depends on both x and y. So we want to eventually solve this, and we'll do that shortly, but let's just write the structure of these two equations. So this means that dx dt is only a function of x, and dy dt is a function, some other function, not the same one. It's obviously different than this one up here, but that's a function of both x and y. Notice that neither of these depend on t. And we're going to keep it that way for a while, because once you start involving t in those equations, things can get a little bit more hectic. So there's our model, and now we're thinking, well, how do we solve this one? Because in order to know anything about solving dy dt, I have to know what x is. But the beauty of having a partially decoupled system is that I could solve dx dt first, get x, and then substitute that function in for x down here. So we're going to do that in just a moment here. We're going to say, first, step 1 will be solve dx dt to get x, substitute x into dy dt, and solve for y. So that's pretty much all we need to do in order for this to take place. We called this a partially decoupled system because the ODE for bucket 1 does not depend on the amount of salt in bucket 2, but the amount of salt in bucket 2 does depend on the amount of salt in bucket 1. If these were reversed, if dy dt was only a function of y, but dx dt was a function of both x and y, then we would call this a still a partially decoupled system. So now we want to solve the system. So we said step 1, solve dx dt, and dx dt was the 0.75 0.75 minus 0.6x. And we have a lot of different options with which to solve this. We could use integrating factors. We could do separation of variables here. We could use Laplace transforms. We have any number of ways that we could solve this equation. And for just the demonstration, keeping this video relatively short, I'll just say I'll provide you with what this comes out to. And if you were to solve this guy, we would end up getting x of t is equal to 1.25 minus 1.25 e to the negative 0.6t. And for this equation, we also have that our initial condition, x of 0 equals 0, because we're told that the first bucket just has clean water initially. There's no salt in it yet. So you could do separation of variables on this. You could do Laplace transforms. You could do integrating factors where your a of t is negative 0.6 and your b of t is 0.75. But either of these, any of these methods would work to solve this. So step 2, we said that dy dt is equal to 0.6x minus 0.6y. And our initial condition is this bucket is also clean of salt. So now we're going to replace x. We're going to replace x right here with what x equals, which is this whole thing. Now we wrote x of t, but that's the same thing as x. X and y are functions of time. That's just implied in the process. So if I do that, I get dy dt. Oh, that's a little bit thick there. We get dy dt is equal to 0.6 of 1.25 minus 1.25 e to the negative 0.6t minus 0.6y. Okay, so perhaps we'll go ahead and solve this equation. Here we could use, again, Laplace transforms. We could use separation of variables because now we have a time term. We can't factor out the function of t. So if I do a little bit of distributive property here, and I get dy dt equals 0.6 of 1.25 comes out to be 0.75, and I'm going to write these in order like this. Negative 0.6y, and then 0.6 times negative 1.25 will be negative 0.75 e to the negative 0.6t, and then we have this 0.6 times 1.25, which is plus 0.75. So once again, Laplace transforms will work just fine here. We could solve that. Let's just go ahead and do it to at least say we did some calculus here in this problem. So we'll take the Laplace transform of both sides. We'll get the Laplace of dy dt equals, and I'm going to write this all out in one step, negative 0.6 Laplace of y minus 0.75 times the Laplace of e to the negative 0.6t plus the Laplace of 0.75. And so this will give me s Laplace of y minus my initial condition. My initial condition is 0. And here I'll have negative 0.6 Laplace of y minus 0.75 times 1 over s plus 0.6, and then plus 0.75 over s. Now I'm going to do a few steps here in one fell swoop. I am going to move the positive 0.6 Laplace of y, or add the 0.6 Laplace of y to both sides, and factor out the s minus 0.6. Back up here real quick. And so we'll write Laplace of y times s plus 0.6. This is just a 0. So now I'll have equals negative 0.75 over s plus 0.6 plus 0.75 over s, and I'll divide the s plus 0.6 over. So once I do that, I get Laplace of y equals negative 0.75 over s plus 0.6 times s plus 0.6. And then I'll have plus 0.75 s times s plus 0.6. All right, we'll do some partial fraction decomposition here, and we will get this expression down here. Now, it's not super common that we get the same binomial factor in the denominator, but you see that negative, oh, and I just entered the whole expression because I knew I needed to do partial fraction on this entire thing, and Wolfram Alpha does a pretty good job of being able to split it up. So you can see this one got split up into the first and third term here, but this negative 0.75 over s plus 0.6 times s plus 0.6 did not get split up. So we're going to have to find a different Laplace transform for that, and the Laplace transform that we will take a peek at is, I'll show you in our, well, first of all, let's go ahead before we move to that middle term. Let's focus on just inverting these two guys, and I'm going to kind of skip a couple steps here. We'll invert both sides, and the inverse of this guy will end up being negative 1.25 e to the negative 0.6t. I hope you're getting comfortable with doing these guys that way. And then the third term, the 1.25 over s, its inverse Laplace, so this is the inverse of 1. The inverse of that one will just be plus 1.25. But this one's kind of weird because we have s plus something squared as a quantity, and that does not partially fraction decompose anymore. So I'll show you one that we haven't used yet. Sometimes you're going to need to bump into these, not very often, but just to show you which one we're actually using here. In this table of Laplace transforms, if you take a look at the denominators, so some of these have s squares in them, and then the whole quantity squared, that's obviously not what we're looking for. We just want a situation where it's s plus or minus some quantity squared. We can't really use this one because b would be 0, and if b is 0, then you end up getting 0, so that's not gonna work. But if you take a look at this one down here, here we have that t to the n, e to the at would be n factorial over s minus a to the n plus 1. So I'm going to screen snip this one real quick here, and we'll grab number 23, and we'll see how that's going to fit and resolve our problem that we have right now. So we'll jump back over to our systems, and we just said that the appropriate one is kind of messing with me here. Okay, so here we have it, and we first of all can think about this negative 0.75 as being factored out. So I'm going to factor that out and think about this as 1 over s plus 0.6 squared. And you see how this matches up. Here we're saying that our n plus 1 is equal to 2, and therefore the n in this equation is going to equal 1. So that means that if I want to work backwards and take the inverse of this, this should be a 1 factorial up here, which it is, and that should invert into t to the n, so t to the first power, e to the at. Well, it's s plus 0.6, which is the same thing as s minus negative 0.6, and therefore whatever sign you see down here, it's going to be the opposite sign up here. So if we have a plus 0.6, this is going to be a negative 0.6. Negative 0.6t. So that means that the inverse of that second term is going to be negative 0.75, that's the coefficient I factored out, times t e to the negative 0.6t. And that's our final solution for y. As you can see, it does require a little bit of complexity. It did require quite a bit of work to get there, to solve a completely or partially decoupled system. Later on, we'll see that there is a much faster way to do this, but for now, this is what we've got. So taking a look at the solutions, again, we just want to analyze this and say, well, there's bucket 1, and we can see that bucket 1 is filling up with salt faster than bucket 2. And the reason for that is because, well, bucket 1 is the recipient of all the salt, and then it has to slowly drip over into this other bucket that's initially clean. So it takes a while for that second bucket to catch up. We can see here that there's a saturation point because we're only filling up at a rate of 1/4 pound per gallon. Out of 5 gallons, that's going to be about 1.25 total pounds that you'll end up getting in there to achieve that concentration. So these things begin to level off. And it's a pretty cool analysis. So that's a partially decoupled system. The other kind we have is a completely coupled system. And this is one where the rate of change of both dependent variables depends on another dependent variable. So this, in our analogy with only 2 differential equations, this is going to mean that dx dt is going to be a function of both x and y. dy dt is going to be a function of both x and y. Now this is the most robust type of system to analyze because, and I shouldn't use f of x here, I should use g of x to say that they're not the same function. So this is the most robust type of system to analyze because it accounts for the possibility that both variables are present. But it does add a monkey wrench to our solution process. Let's again take a look at a model. Learning to model in differential equations is important. Suppose we have 2 species. Each one preys upon the other. Each of the creatures in species 1 eats, on average, 3 of species 2 each day. Each of the creatures in species 2 eats, on average, 1.5 of species 1 each day. Initially, there are 500 of species 1 and 750 of species 2. Write a system of differential equations modeling this scenario. So let's let x denote the number of species 1. I didn't want to say what these were because I couldn't think of any 2 creatures that eat each other, but maybe you can, maybe you have one coming to mind, but I couldn't, so I just decided to just refer to them as species. So, and then this is going to be the number of species 2. And we want to model the rate at which species 1 is changing. Well, first of all, we know that it's going to be the we don't know how quickly they reproduce, and so we're just told the rate at which they're eaten. So dx dt from the given information will only be the rate at which they are eaten. So rate at which they are eaten. Okay, so that's going to be a negative rate of change because it's going to lead to a decline of this species. Again, we're not accounting for reproduction or anything like that. We're just looking at a simpler version of this, just so that we can see how these models are going to depend on each other. Okay, well, what do we know? We know that species 1 eats on average 3 of species 2 each day, so that's not going to affect, as far as we know. Now that'll help them reproduce, obviously, but that's not going to affect the rate at which x is changing. But each of the creatures in species 2 eats on average 1.5 of species 1 each day. So if we look at the units of this, we know that this should be species per day. And so we know that species 2 eats on average 1.5 species 1 per day. But we want the units of this to be in, and that this should actually be not species, that's not how many species 1 there are going to be per day. That's how many species 1 each species 2 is going to eat. So per one species 2. And that's for each 1 day. So that's how many of the first creature, each of the second creatures will eat. But in order to end up with species 1 per day, which is what the units of dx dt should be, I have to multiply it by how many species 2 there are. Well, there are y of them. At any moment there are y species 2. And so now when I multiply those together, I get the rate of change of species 1 per day. So my dx dt will be actually, negative, right? Because there will be a decrease of that many species, and that will be negative 1.5 times y. So we didn't really have to do the heavy dimensional analysis. We could just say that the rate at which species 1 is changing is a decrease of the 1.5 that are eaten by each of species 2 per day multiplied by how many there are. So if there are 100, e.g. if y is 100, then that means each of those 100 species 2 are going to eat 1.5 species 1 on average, and so that means that the X population should decrease by 150, right? Because all 100 of them are going to eat on average 1.5. Some will eat 2, some will just eat 1, but we would expect them to eat up that many of them, and that would be the reduction in the population. Using a similar line of thinking, dy dt will be negative 3. They're going to eat each of the species 1 is going to eat 3 of the species 2. So if there were 100 of species 1, then the population of y would decrease by 3 each day. By 300 each day. And then the last thing we want to note is just what's the initial condition. So x of 0 is given to us as 500, and y of 0 is given to us as 750. So you can see that here, if the reason this is called a completely coupled system is because the population of x, if you think about it, in order to calculate the rate of change or to solve this guy, I need to know the value of y. To solve dy dt, I need to know the value of x. And so you can see that these are completely coupled because they both rely on each other. And more formally, we would state that this system is not quite as easy to solve, since we would need to solve for x of t in order to get y of t. But to get x of t, we need to solve y of t, which is circular logic. So to solve, for example, dx dt, I need to know what y is. So I go over here to dy dt and I say, let me solve for y, but this requires us to know what x is, and so we have this circular logic. It turns out there's a really nice way to solve this type of system, but we're not going to do that here. We'll do that in a separate lesson. So as a final approach, we'll think about how we can start visualizing these systems of ODEs. When we studied single ODEs, we used slope fields, and we plotted a bunch of slope vectors on the ty plane. But now we have 3 variables. We have t, x, and y. And so because we have 3 variables, we can't really create a 2-dimensional plot. And we really don't want to do 3D plots because those can be difficult to understand, especially if they're vector fields in 3 dimensions. They're very hard to look at. We're going to limit ourselves to just autonomous systems. So autonomous systems are where the rate of x only depends on x and y. Remember, for an autonomous differential equation, it's an equation where the rate of change of a variable only depends on that dependent variable. But for systems, those can depend on both x and y. Notice there is no t. It does not depend directly on t. And so we're going to make an important observation. dx dt can be negative, positive, or 0. And dy dt can be positive, negative, or 0. Now you'll see why that is important here in a moment. Consider a graph in which we plot x of t versus y of t. At each xy pair on the graph, we can generate a value of dx dt and a value of dy dt. So if I have a system of equations like this, and you give me an ordered pair, an x and a y, I can plug those into the right-hand side of the equation, calculate dx dt, plug in x and y into the right-hand side of dy dt, get a dy dt, and then plot those two vectors at that point. So I'll plot two vectors, one for dx dt, one for dy dt. Then I'll draw one final vector that whose slope will be the comparison of dy dt to dx dt. And if you see that this ratio right here, the dt's cancel, and you're left with dy dx. Notice that this resultant vector is what is expected to happen in 1 unit time. We repeat this process for many such points, and the final graph we get is called a phase plane or a phase portrait, and it shows us how x and y co-vary over time. Let's do an example. Produce a dy dx vector at 1, 0 and 1, 1 for the system. Dx dt equals x plus 2y, and dy dt equals negative x minus y. Okay, so at the point 1, 0, we're going to have two vectors. So here's 1, 0, and at the point 1, 0, we need to generate a dx dt and a dy dt. So we're going to generate both these slopes. To get the dx dt, I have to take 2x plus y. That was our differential, or sorry, x plus 2y. So the x value is 1. 2 times the y value, that's 0. That gives me an output of 1. To calculate dy dt for the point 1, 0, that's going to be negative y minus x, or negative x minus y. So that's negative 1 minus 0, and that comes out to negative 1. Okay, so at this point, I'm going to plot two vectors. So dx dt tells me that in 1 unit of time, I expect x to increase by 1. So let's go ahead and do that. So there's my dx dt, and that means in 1 unit of time I expect x to change in one unit. This is because x is positive. Earlier we were trying to make the observation that dx dt could be positive, negative, or it could also be 0. So in this case, dx dt is positive, which means in 1 unit of time, I expect x to increase. Okay, so x is going to increase by 1. So this is my representation of dx dt equals 1. Dy dt is negative 1, and that means I expect y to decrease by 1. Okay, well, the y-axis is this axis here. The x-axis is this axis here. So to have y decrease by 1, that means y is going to go down this way. Now this is again in 1 unit of time. So in 1 unit of time, if x moves to 2 and y moves to negative 1, then the result, or the resultant vector, is that we will end up at this point here, right? So x will increase by 1, then y will decrease by 1, and we'll expect our vector to point down here. So this blue vector is dy dx. That's the change in y per change in x. So the slope of this line is really negative 1 to 1. Negative 1 rise to a positive 1 run. And the problem wants us to also repeat this for the point 1, 1, which is this point here. And I'm going to do exactly the same thing. I'm going to calculate the dx dt at that point. Dx dt is going to be x plus 2y, which is 1 plus 2 times 1, which is 3. And the dy dt at that point is going to be negative x minus y, which is going to be 0. I'm sorry, not 0, negative 2. So that will be negative 2. And so once again, what I'll do is I'll plot two vectors. And one of those vectors is going to, well, my x vector is saying that x is supposed to increase by 3 in 1 unit of time. So to increase by 3, well, that means we'll go from 1 all the way over here to 4. Sorry, that doesn't look real great. That's dx dt is going to increase by 3. My dy dt is going to decrease by 2. So Actually, that would put me at the same point down here, and that's dy dt equals -2. And so as a result, my resultant vector is going to point, well, if x goes from 1 to 4, but y goes from 1 down to -1, that means my resultant vector is going to point right there. And that's my dy dx is y going to decrease by 2 as x increases by 3. So the slope of that line is -2/3. Now this is going to be very tedious because we have to do this, generate two vectors, create the resultant vector for all of these points. And also notice that this vector here is longer than this vector here. So you can probably imagine that some of these vectors are going to start to intersect one another. The green and the pinkish vectors are not ones that we actually want on there. Those just assisted us in helping the blue vector, which describes in 1 unit of time what's going to happen to those two populations. So what we'll do is we'll shrink these down proportionally so that this longer one will still be longer even after we shrink it down. So maybe we'll take like 1/10 of it and we'll shrink it down. We'll take 1/10 of this and shrink it down. And repeat this for many, 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 many points. We get something that looks like this. And you can see that right around the point 1, 1, which is right about here, we see that there are vectors that point right and down. And that was because dx dt was positive and dy dt was negative. The vectors should point to the right and down. If we had done this over here in the fourth quadrant, you see that these vectors, like this guy here, points to the left and a little bit up. That would mean that dx dt, well, x is decreasing, because this is the x-axis, and that means that y is increasing because the vector points upwards, and this is the y-axis. So I probably should be careful about my labeling here, but this is the x-axis and this is the vertical y-axis here. So if we generate this for many points, you can see what's happening here, that there's sort of this flow, and x and y seem to be sort of flowing into these elliptical shapes as time passes. And again, this is just repeating our process up here for many, 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 many points. This little applet, if we go over to this site, will allow you to generate this slope field. Let me just show you. So here's what this looks like, and you can see it allows you to enter x prime, which is the same thing as saying dx dt. So I had to do x plus 2, and then a multiplication sign is necessary, times y, and then negative x minus y, and then I just set my display here. So you can see that some of the arrows are a little bit longer because in 1 unit time, in some locations you're going to have bigger changes in both x and y than in others. You can see this guy is a little bit shorter than, say, this guy over here is a tiny bit longer. And so that's just because these represent what's happening in 1 unit of time. So actually I can click on this plot, and what this does is it just generates using a numerical method, kind of like Euler's method, similar to that. It just generates a lot of points and then connects them. And you can see depending on what initial condition I pick, the oval just changes shape. So x and y seem to be cycling over and over and over again in this elliptical fashion. So I can remove those and I can just look at one. And you can probably kind of sketch that out in your head what that would look like. So if I picked 1, 1, you can kind of see that would be an elliptical mode. But if I click on around 1, 1, it'll generate the full-on curve. So it's kind of hard to see just by the vectors, but you can at least see the flow of how x and y are going to change over time. So let's say that what we wanted to do is we wanted to sketch what x and y would do over time. That is, again, keep in mind that time is not in this graph. The only representation of time that we have here is how long these vectors are, because each of these vectors, once again, represents what happens in 1 unit of time. So, even though we can't necessarily solve this equation, we can kind of see what's happening to x over time. The time axis we're not really going to label because we don't have any sense of time in this graph. But I started off with the point, my initial condition was the point 1, 1. That's what we wanted in the problem description up here. Sketch a y versus t graph and an x versus t graph by using the phase plane above. For x of 0, y of 0 equals 1, 1. The t-axis cannot be accurately labeled, but the x and y axes should show key values. So how can we do that? Well, so we know that x and y both start at 1, 1. And maybe actually instead of doing x first, I'll do y first, because that's a little bit easier to visualize. So here I have y over time. So what's y going to do over time? Well, first of all, y starts at a value of positive 1. So let me zoom out just a little bit here so we can see this a little bit more distinctly. So y starts off on this axis, that's my y-axis, starts off at positive 1. So the first thing I'll do is I'll come over here and I'll say, okay, y starts off at positive 1. Well, what does it do next? Well, we see that the orientation is in this direction, so the points are going to, this point, if we pressed play, would just circulate around this ellipse. And so what is y doing on this interval? Well, from here to about here, the y value decreases, right? So up until about here, y continues going down, and then from there, y starts to go back up again. So you have to visualize this in 2 dimensions. So from here down to this point, right about here somewhere, the y value is going down. The y component of that ordered pair circulating around here is going down. Now from here to about, where is it? From now y is going to be on the rise. If we continue to trace this point along here, this y value would increase until it hit about that location. And then from there, we see that from this point to this point, y is going to come back down. And that's just going to repeat over and over and over again. So where does y go? Let's think about this. So y starts off at 1 and then decreases down to just under -2. So we'll just call that about -2 1/4. So in this graph, I can plot, at some point in time, here's -1, -2, -2 1/4. I'll just put it right about there. Okay, so there's -2 1/4. And from there, that point starts to go back up until it rises to about positive 2 1/4. Again, I have no semblance of time here, so I'm just trying to eyeball this and say, okay, so about here we'll say it reaches 2 1/4. Now it's not going to be straight lines, right? These are smooth curves, so in all likelihood it's going to look something like this. Okay, and then once it reaches that third point, or it goes from here to here to here, now it's going to arrive back at its starting point, which this was an x value of 1. So next we expect this graph to decay back down to 1. I don't know, again, how long this is going to take, so I'll just draw it there. And again, kind of a smooth curve takes us back down. And you can see that this is going to be periodic because now the same thing is going to happen. Function is going to decrease back down to -2 1/4, come back up, and so on and so forth. It's not necessarily going to be a perfect sine or cosine function, but it will be periodic. Now x of t is pretty much doing the same thing, except x starts off by increasing. Remember, x is in the right-left direction. So let's clear off some of this. Actually, maybe I'll just use a different pen. Okay, so from this value, x is going to, the point moves along here, and x is increasing, x is increasing, x is increasing, x is increasing, until about this point, x increases. But then from here, as we start to move along the curve, you can see that if we're keeping track of the x-axis, that value is decreasing until it hits about here. So from there to there, the x value is decreasing. And then the x value continues increasing along here. X is getting bigger, x is getting bigger, x is getting bigger, x is getting bigger, x is getting bigger until it hits this point. So here x starts off at 1 and then moves to a point that's just slightly bigger than 3. Again, I'll just pin it right about 3.2 or so. So x is going to start at 1. X is going to start at 1. So there's 1. and then it's going to increase to about 3.25, we said. Next, after that point, x begins decreasing until it hits about this x value here, which is about, again, negative 3.25. And from there, it's just going to increase back to 3.25, decrease back to 3.25, and repeat that process ad nauseum. So here we're going to then eventually decrease to negative 3.25, then increase back up. And on our way up, we're going to pass our starting point again. So maybe it's going to look like this. If we just wanted to graph one period of this, it would look something like that. And then it would come back up to 3.25 and then go back down, and repeating this process indefinitely. So even though we couldn't solve this differential equation, the point is we could try to get a sense of what is happening to x and y over time. And this is really all we needed to do is generate a phase plane, and from there we could extrapolate. So if we were just interested in just understanding how x and y behave over time, this phase plane would do us a great deed. So we'll go ahead and stop here at this video. It's already getting really long. So this just introduces the concept of differential equations. In the next lesson, we're going to get into working with some of the linear algebra basics before we start really attacking some of these completely coupled systems.